So, in the last class we were discussing about the fuzzy relations. We defined this fuzzy relation from a product space, suppose x to y, like this. This I already defined in the last class. R bar is equal to x y and the membership function of this relation R or R bar x y, such that this x y belongs to x cross y. Okay? This we had defined in the last class, when R bar is a relation from product space x to product space y. Okay? And I wrote one example that is about the temperature and pressure. So, let us take that example, and moreover you see if I write mu R bar, what is this? This is membership degree x y. This we actually defined as mu A cross B or A bar cross B bar, where A bar and B bar are the subset in product space x and y. Okay? X y, and this we defined as minimum of mu A bar x, mu B bar y. So, this way we find the membership values for this mu R bar x y. Okay? So, we had the example as A bar is equal to 0.2 by x1 plus 0.5 by x2 plus 1 by x3. Okay? And B bar we had 0.3 by y1 plus 0.9 by y2. Okay? So, this is in capital X, this is in capital Y. Okay? Then I can define, I can form the relation matrix here like this R bar. So, I will write first this 0.2, 0.5, 1, this is your 3 by 1, and this for y, that is 0.3, 0.9, this is 2 by 1. Okay? Then we form the matrix as 3 by 2. Okay? For this I will write as x1, x2, x3 and y1, y2. Okay? Now we will have 0.2, 0.3 minimum is 0.2, 0.2, 0.9 minimum is 0.2, 0.5, 0.3 minimum is 0.3, 0.5, 0.9 minimum is 0.5, 1.3 it is minimum 0.3 and 0.9. Okay? So, this is the relation matrix that we get for temperature pressure relation. We told yesterday this is your temperature, this is your pressure. Okay? So, temperature pressure relation is this using this definition. Okay, very simple. Take the minimum values of this. Okay? So, we will take more examples afterwards, then it will be more clear. Okay? Now, with this, now I will define three definitions, that is first projection, second projection and total projection. So, remember this we had defined relation from product space x to product space y. Now, we define first projection as, and we denote this by R bar 1. This is your first projection and we define this as x and maximum of mu R bar x y in y, and such that x y belongs to x cross y. So, we will take example, then we will see what is this. Okay? It will be more clear when we will take the example. First projection is defined as like this: x comma maximum of mu R bar x y on all y, where x y belongs to x cross y. Second projection, similarly we write or denote like R bar 2 for second, and now this is just alternate. This is y maximum of x over x mu r bar x y such that x y belongs to x cross y. This is your second projection. Okay? Similarly, I have total projection, and we define or denote this by r bar t, and this is the combination of these two, and we write like this: max over x, maximum over y, mu r bar x y such that x y belongs to x cross y. So, these are the three projections. Now, let us take one example and see how we get these and what you get. Okay? Suppose I take the example as, suppose I have this relation given for x1, x2, x3 and y1, y2, y3, y4, y5 and y6. This is your x, this is your y. I have y1, y2, y3, y4, y5, y6, and these are your x values. So, these are all membership functions. Remember, so these are given as 0.1, 0.2, 0.4, 0.8, 1 and 0.8. x2 for different y, it is given 0.2, 0.4, 0.8, 1, 0.8, 0.6. x3 for different y given 0.4, 0.8, 1, 0.8, 0.4, 0.2. So, this is the relation given. Now, let us find the projections for this relation. This relation is from product space x to y. Okay? Let us find, you remember these definitions. And for first projection, we denoted by R1. Okay? R1. So, here I will write the membership function for R bar 1. So, see, it was x maximum y. That means, what will be here? 1. What will be here? 1. Here 1. This is your mu r1. These are the projections. Similarly, for here, second mu r bar 2, this is 0.4, 0.8, 1, 1, 1, 0.8. First projection, second projection. So, what will be total projection? If you remember, total projection was all max and for on x and y. So, what is that value? 1. So, this is your total projection. Okay? In this way, I can find first projection, second projection and total projection for any relations given. By chance, here it is coming 1. Okay? It depends upon what are the membership values are in the relation. Okay? Very easy. So, now let us take relation and find intersection and union. That is also very easy. So, let us take one example. We are given two relations. Given S is a relation. It is from x1, x2, x3 and y1, y2, y3, y4. Okay? So, y1, y2, y3, y4 and x1, x2, x3. So, these are given as 0.8, 1, 0.1, 0.7. First row 0, 0.8, 0, 0, 0.9, 1, 0.7, 0.8. Okay? So, this is S bar, or let us take this is as R bar, same whatever you can take, and S bar is your again x1, x2, x3, y1, y2, y3, y4, 2, 3, 4. We have 0.4, 0, 0.9, 0.6, 0.9, 0.4, 0.5, 0.7, 0.3, 0, 0.8 and 0.5. Now I want to find first R bar intersection S bar, intersection of these two relations. You know the definitions I wrote in the last class. So let us have this x1, x2, x3, y1, y2, y3, y4. So what was the definition? Very easy. Minimum of this and this, that is 0.4. So you can yourself complete 0 and 1, 0, 0.9, 1, 0.1, 0.1, 0.7, 0.6, it is 0.6. Very easy. 0.9, 0, 0, 0.4, 8, 0.8, 0.4, 0.5, 0, 0, 0.7, 0, 0, 0.3, 0.9, 0.3, 1, 0, 0, 0.7 and 0.5. Just take the minimum. Similarly, I can have R union S bar and take the maximum. Okay? So, all the maximum entries you will have here, and that will be your R bar union S bar. Okay? So, as you know in crisp relation, the composite relations, remember? So, I am doing directly fuzzy composite relation. Okay? What was that? Composition actually, composite or composition of relation. Okay? What was that in crisp set theory? Composition means what? Composition of relations. Suppose I have a product space X, I have product space Y, I have product space Z. Okay? I have relation from X to Y, Y to Z, then what is your X to Z? So, X to Y actually this is your X cross Y, that we are doing now. This is your Y cross Z, so X cross Z, that we have to find. Means I have a relation, suppose R and here S, then what is R bar S bar, that we have to find. And for these we have three methods, very simple, only max mean type you have to take. Okay? So, let us have that. So, first one, it is called max mean composition. Second one is called max product composition. Third one, it is called max average composition. And in general, we actually practically we use this max mean composition. Okay? So, let us do that. What is your max mean composition? Okay? So, if we have two product space x2 means 3 x2y y to z. So, x2y, suppose I have a relation R bar. Okay? So, R bar I can define as, because this is from x to y. So, this is x y comma mu R bar x y such that x y belongs to x cross y. This is your R bar. from x to y. Now, if I say y to z, it is s. So, we will write then what? Y to z. So, I will write yz comma mu r bar yz such that yz belongs to y cross z or not? Is it okay? Mu s bar, yes, thank you. Mu s bar, because I have taken s bar here. Okay, that is no deal. I can take R1, R2 also. Okay, so r bar, it will be s bar. This is the relation from y to z. This is from x to y. I want to find x to z using first this max mean composition. So, the procedure is R S, that means R max mean S. Okay? The elements will be x z, and we have mu of, I have to combine such a way. So, I have to combine by max mean, means I will write max on y and then mean mu r bar x y and mu s bar y z. Understood? Main is our this membership degrees or values. Okay? So, I will take one example, then it will be more clear. Maximum over y and minimum of all those mu r bar x y, mu s bar x z, sorry, y z. Okay? So, this is your max mean composition. Okay? Means given r and s, how you composite this r o s or r bar o s bar. Okay? So, let us take one example and see how you can find this composition. Okay? And that is also very simple. So, let us suppose we have r bar as we have x to y, x1, x2, x3 and y1, y2, y3, y4, y5. Okay? So, y5, y4, y3, y2, y1. So, what are the membership degrees? 0.1, 0.2, 0, 1, 0.7. First row 0.3, 0.5, 0, 0.2, 1, 0.8, 0, 1, 0.4, 0.3. Okay? And suppose I have S bar as from now y to z. So, I should have from y to z some matrix, relation matrix. So, we will have y1, y2, y3, y4, y5, and suppose z values are z1, z2, z3 and z4, 4 values. Okay? So, then relation matrix I will have like this and y this. Okay? So, these values are 0.9, 0, 0.3, 0.4, 0.2, 1, 0.8, 0, 0.8, 0, 0.7, 1, then 0.4, 0.2, 0.3, 0, 0, 1, 0.8. Okay? I want to find R max mean S. Okay? So, see, what is the procedure? What is the procedure? I have to take first minimum. Minimum, let me write, then I will explain. I have to take minimum of what? Mu r bar x1 y1 and mu s bar y1 z1. Mu r bar x1 y1, mu s bar y1 z1. So, what is that? Minimum of 0.1 and 0.9. Is it okay? that is your 0.1. Okay. Then again I have to find minimum of mu r bar x1 y2 and mu s bar y1, yes, is it not? x1 y2 y1 z2. So what is that? 0.2 and 0, that is 0. Understanding? Then let me write first this row only, then you can do, means you will understand what is happening actually. Minimum of mu r bar x1 y3 and mu s bar y1 z3. Is it okay? But we are doing wrongly. We are doing wrongly. From here it is wrong. See, mu r bar x1 y2 that was okay, and mu s bar y2 z1. It is like, I am telling, it is very easy, like matrix multiplication you see. Okay, how you multiply? This into this, this into this. So that way you get the product matrix, product of two matrices. So you just think about that, but take minimum. Okay. So now that means, that's why I am telling, so x1 y2 it should be y2 z1, because this thing should repeat y1 y2, that was not repeating there. Understanding? So it should be y2 what? z1, and then it is what? 0.2 and 0.2, so it is 0.2. Is it okay? So this way you can write all minimum of mu r bar x1 y3, no, and mu s bar y3 z1. So that means 0 and 0.8. So it is 0. Looks very simple, okay, but while calculating you may do mistake, okay. So that's why be careful. So minimum of mu r bar x1 y4 and mu s bar, it should be y4 and z1. So what is that? What is that? x1 y4 and y4 0.4. So it is 0.4. Then last one for this only, minimum of mu r bar x1 y5 and mu s bar y5 z1. What is that value? 0. I believe you. So I am writing 0. I am not seeing. Okay. This should be 0. Okay. Now you have done one portion, means the minimum you have found. Now I have to take maximum of this. Then you will get the first entry of that r dot s. Okay. So now I have to take maximum of 0.1, 0.2, 0, 0.4 and 0, and this is 0.4. Okay. So that's why it is max min. So this you got first one entry, as you got in matrix multiplication also similarly. Okay. So if I do all these calculations now, this, first row, third column, first row, fourth column. So you will get r dot s first row. Understood? For the second row, you will have this, second row, first column, second row, second column, second row, third column, second, just that you do in matrix multiplication. So I am writing the solution directly. Okay. So you can complete that, and you will have r dot s. R, what was that? Solution. So you can tell me x1, x2, x3, it will be from x to z. Okay. So that is your z1, z2, z3, z4. Okay. So first one we got 0.4. So it is 0.4. Next, I hope you will get 0.7, check this, 0.3, 0.7, 0.3, 1, 0.5, 0.8, 0.8, 0.3, 0.7, 1. Okay? After doing for all these rows, you will get this. This is your composition from R to S. Okay? Means from X to Z. Okay? Now, actually what is happening? See, I have the relation matrix from X to Y. So, if I draw the diagram, so I have X1, X2, X3. Okay? And Y values we have Y1, Y1, Y2, Y3, Y4 and Y5. These are the 5 values, these are the 3 values. So, now for each connections you have the strength, means if I connect this X1, Y1 like this, okay, the strengths are 0.1, 0.2, 0. So, X3, X1 and Y3 should not be there. This relation is not there. Okay? So, I have this diagram for X1. Similarly, I have X2, all this, you connect that like this. So, X2, again X3 is not there, X4, X5, and these are the weights, means strengths. So, actually this says that how these are related to all variables. Now, Y to Z, Z is your Z1, Z2, Z3, Z4. Now, this again Y1 to Z1, Y2 to Z, Y1 to Z2 is not there, 0, Y2, Y1 to Z3 it is there, and Y1 to Z4. So, we have these strengths as 0.9, 0.3, 0.4. So, actually in composition what we are doing? We are going from X1 to X to Z using max mean principle. Okay? So, if I now write the max mean one like this, so what you will get? X1, X2, X3 and Z1, Z2, Z3, Z4 and the strengths that you have got after composition like this. Means you can draw that here X1, X2, X3, Z1, Z2, Z3, Z4, connect that, here no zeros are there, so all are related. So, you are seeing from one space to another product space, you are going from X to Y, this is the relation, Y to Z, this is the relation, and you have some no relation also you have. Okay? Now, after composition, so suppose this is pressure, temperature or wind. So, pressure to temperature I have these relations, temperature and wind may have these relations or some other variable, depends. So, now what is between pressure and wind? Okay? So, then pressure and wind I can have like this.
So, there is no relation between X3 and Y2. How do you get relation between
X3 and Y2. Yes, then
how do you get relation with X3 and Z1?
X3 and Y2 and Y2. See, because we do not have X3 and Y2, but you may have, na? You may have. Okay, I may not have with your relation, but your elder brother I may have the relation or not. I may have, means I am just giving example, I may have zero relation, but his elder brother I may have, means, but in fuzzy sense may have then 0.1 relation, with him may be 0.8 relation, he may be my friend or something. Okay? So, like that you may have, you are understanding. So, it is not that suppose in electrical circuit also one is fail, so other one may not fail using this type of relations. So, those are very important actually in everything, everywhere, means high value means electronic circuits or whatever. Okay? So, they are actually, if one is failed, so other one is there to support. Okay? So, like that, those are actually you can visualize if you see that practically in practical application. Mathematically you are correct, how this is 0 and but we have the relation there, means when we do for X3 to Z4 or something. Okay, but it may happen. Understand? Okay, so this was for first one, that is max mean. Similarly, we have max product and max average, those are similar to this, only the definition is changed. Same, you have suppose R and S, R bar and S bar, you have to find R dot S bar, R bar dot S bar, with some little bit change, that those two definitions I will write and those you can do yourself, that R dot S. Okay? So, with this same example, we will complete those two operators. So, I am writing those two operators only. Okay? So, second one was max product, max product. So, here it is defined as R bar dot S bar, and because it is product, I am writing in below dot to distinguish. Okay? Dot is equal to x z, because after composition it will be from x to z, and max product. So, we will take max on y and then product of the membership functions. There it was minimum, so I took minimum, max mean, here max product. So, product means mu r bar x y and dot, dot means product, and mu s bar y z. Okay? And I should write there, I forgot to write, x belongs to x, y belongs to y, and z belongs to z. This one should write for the completeness. Okay? Okay? So, this is the same, you have R, you have S, there we are taking minimum, here product, then take the maximum, you will get the relation. Okay? Then we have third one, max average. So, you have to take average. So, that means you have R, here I will write AV for average, okay, is equal to x z, and we will have max y, and I will write half average mu r bar x y, or you can take inside also, no problem, plus mu s bar y z, and x belongs to x, y belongs to y, z belongs. So, here what you will do, you will add and take, then divide by 2 for R and S and form the R O average S bar. So, these are the three operations for your composition. Okay? So, today we will complete here. So, next class we will do further, okay, on relations only, fuzzy relations. Thank you.